The previous chapter was on reflection, and this is about refraction. That is the second and last chapter in optics. In refraction, we are going to learn about why light bends. Light doesn't always travel in a straight line. What is a law governing refraction? Concept of refractive index, the phenomenon of total internal reflection, and the types of lenses that do refraction and the lens formula. And we'll relate it with lots of practical examples. So to see refraction in action, here are two pictures. Pencil appears bent. It is not actually bent, it is a straight pencil. Part of it is in water, part of it is in air. And look at the shape as it appears to be. It seems light is no longer traveling straight. In the previous chapter, we said that ray of light goes in a straight line and so on and so forth. That is all right when the light is traveling in the same medium, which is also homogeneous in nature. That is, the nature of the medium doesn't change from point to point. If the medium changes, like a ray of light goes from air to water or from water to air, then light bends, and that is what is refraction. Another example I can talk about is there's a coin here placed in a glass which is empty. A person has fixed his eye like this, so a ray of light right at the bottom corner of this glass can reach this person's eye. We see something when a ray of light from that particular point reaches our eye, either directly or by reflection. So he's able to see that point, but he's not able to see this coin, this black coin, because any ray of light, say this ray of light that goes like this, doesn't hit his eye, it goes like that. And in fact, this is even worse. This ray is even worse because it goes like that. So he's not able to see the coin. Pour some water without changing your position. And we have poured water up to some height. Now, apparently, the coin is lifted. Apparently, the coin is not actually lifted. The coin is heavier than water. It stays wherever it was. But the coin appears to be lifted, and now a ray of light from the coin reaches the eye. This is also refraction. Refraction means bending of light. If I have a source of light, say O, at the point O, and I've drawn two rays, one is falling perpendicularly on this air glass interface. I have put a rectangular glass slab in its path. So it is starting from air, enters the glass perpendicularly, it doesn't bend. Then again it approaches the glass air interface that also is perpendicular, it doesn't bend. But an oblique ray bends. If I drop a perpendicular at this point, it is bending. Instead of going this way, it is bending like that. And at this end, at the glass air interface, instead of going like this, it is bending this way. In the first case, it is bending towards the normal. In the second case, it is bending away from the normal. Why does bending occur? The fact that perpendicular rays don't bend at all. Here, the angle of incidence is zero. The incident ray is along the normal, so the angle of incidence is zero. So perpendicular rays don't bend, only oblique rays bend. Why do they bend? Due to a change in speed. Those materials that allow light to go through them, they are called transparent, others are called opaque. So refraction is obviously through a transparent medium. And it seems that when light goes from air to glass, its speed changes. That is why it bends. Now there are two questions to ask. Light is an electromagnetic wave. It doesn't need a medium. It doesn't need a medium. But when it does go through a medium which allows light to pass through it, then it changes its speed. Why is that? And second, simply because the speed is changing, why should it change its direction? Those are the two important questions. So let us first address the first part, that is, why does light change speed in another medium? It is coming from air. Actually, air is itself a medium. Vacuum is what we should be talking about. When it comes from vacuum and enters into air, then again its speed changes a little bit. And from air to glass, or air to water, or air to any other transparent material, the speed changes quite a lot. Why does the speed change? Well, there are lots of theories floating around, but they are wrong. One theory is that light scatters. After all, any medium contains atoms, and when the ray of light comes in, it hits the atoms and gets scattered away, and that takes time, and therefore light slows down. But then scattering is a random phenomenon. How can you make sure that after scattering, after suffering multiple scattering, it will go back to the original direction? What I'm saying is that ray of light is coming like this, hits an atom, scatters, hits another atom, scatters, hits another atom, scatters, and then goes like this. Now, this was the original path. How do we know that after multiple scattering events, it will come back to the same direction? It makes sense to say that scattering takes time, the path is more, therefore, more time is taken. That means the speed has become less. All that makes sense. But why will it come back to the original direction? Scattering is a random phenomenon. So that doesn't work. Second theory is these atoms absorb the light completely and then they re-emit that light. And absorption and regeneration takes time and therefore it slows down. That also doesn't work because after having absorbed that light, how does this atom know in which direction the light should be sent? What was the original direction of the light? How does it know that? It has already absorbed it. So it has got no way of knowing in which direction you should be regenerating it. That also doesn't work. And by the way, these two theories are based on the particle theory of light. The particle theory of light, which has a meaning, and there's a more advanced concept of duality of particle and waves. All that is fine, but these two theories don't work. What works really is the nature of light as a wave, which creates this change in speed. Now, briefly speaking, if there are two waves going in the same direction and the speeds are different, then they interfere with each other, producing the resultant wave, which is even slower. Now, when the light comes in, it is an electromagnetic wave, and there are oscillating electric and magnetic fields. For optics, the electric field vector is the important one. So now this electric field that is coming, that is oscillating by itself, and electron is a charged particle. So the electron starts oscillating also. Electron within the atom starts oscillating. And that oscillating electric field produces a second electric field. Now there are two electric fields, one original and the other one that is generated by this oscillating electrons. The interference of these two fields produces a resultant one which is moving slower. So the reason that light slows down is due to the interference of electric fields. But why should it change direction? That is the second part. I mean, I have never seen a bullet changing its direction. If I fire a bullet with some speed v, it pierces through this tree and emerges out. I agree that this will be a lower speed because while passing through the tree was exerting a retarding force, so it slows down. But it doesn't change directions. Purely because the speed has reduced, it doesn't change directions. Why does light do so? And the secret lies in the fact that light is a wave. To understand that, let me talk of the way soldiers march. So here is a group of marching soldiers. The way they march, they have to maintain a certain discipline. There is this first line, then second line of soldiers, then third line of soldiers. They have to march together, so everybody's marching speed should be the same. Second, this line, say the first line is perpendicular to the direction of marching at all times. At all times, this line, all the lines must be perpendicular to the marching direction. That is a very important part of soldiers marching. It is not one soldier marching, it is many soldiers marching, and then they have to maintain their discipline. So let us see, due to this discipline, why do they have to change their direction when they approach another medium? And then I will link up how this soldiers marching is similar to light. Say soldiers are marching, and this is normal land on which their marching speed is normal, and then there's marshy land where they can't march that fast. So the speed is lower here, okay? That is what it means. So I have these soldiers marching. I'm just drawing a top view and a few soldiers marching, and they're all marching in this direction. The line joining the soldiers must be perpendicular to the direction of the marching of the soldiers. All right, what happens when they come to this interface and the interface is not perpendicular, it is oblique? So let me just draw these three soldiers. A time comes when the three soldiers are here. Now what happens? This soldier enters the marshy part. In the time that he walks some distance, this soldier has already come here because his speed is higher. He is on normal land, but this soldier has entered marshy land. There's a transition going on. And please note, this soldier did not change his direction only because his speed was lower. Nobody changes direction just because his speed has become lower. But what happens now is, now the second guy would be somewhere here. Now what happens is all three are now in the same marshy land, and the line joining them has become like this. And they have a discipline that their marching direction should be perpendicular to this. What has happened? They were going like this and they have bent like this. This is the normal at that interface. They have, instead of going straight like this, they have bent towards the normal. So when the soldiers go from high speed zone to low speed zone, they bend towards the normal because they have to maintain the discipline that their direction of marching should be perpendicular to the line joining them. In the reverse case, we have soldiers marching from marshy land to normal land. What happens then? Again, let's see the three soldiers. In the time that this soldier reaches here, this soldier goes much farther because he is on normal land where he can walk faster. Again, he doesn't change his direction purely because the speed has increased. And at this stage, the second guy is somewhere here. At this stage, all three of them are in the normal land. And now they see, oh, the line joining them has become like this, and therefore they should now march in this direction. So while they were coming like this originally, they have bent like this. Instead of going straight like this, they have bent like this. They have bent away from the normal. So this was bending towards the normal, and this is bending away from the normal. High speed to low speed, when they go, they have to bend towards the normal. Low speed to high speed, when they go, they have to bend away from the normal. And Low speed, wherever the speed is low, we will call that medium optically denser, optically more dense, optically, not from mass perspective. And this one will call rarer. So when the soldiers go from a rarer medium to a denser medium, they have to bend towards the normal. And when they go from denser to rarer medium, they have to bend away from the normal. Another example I can give you of a car bending. Here is a car that is coming towards us, and these are the ends of the road. Now, this road is normal, but some construction work is going on, maybe, and this road is bad road. On a bad road, the car has to slow down, right? At this instant, this tire is entering the bad road, but this tire is still in the good road. So, in the time that this tire comes here, this tire will cover a much smaller distance because he is going on bad road. And now both the tires are in the same, and this frame of the car is now bent like this. The frame of the car has bent, so the whole car has actually bent, and now the car has to go in this direction because this frame is perpendicular always to the direction of the motion of the car. This is the car frame, and the car is going like this. Car can't change its shape, but because of the wheels entering the bad road at different instants, what happens is that when both the cars are in the bad roadside, then the frame has tilted like this, and now the car has to go in this direction. So the car was originally coming like this, and this is the perpendicular at the interface. The car has to, instead of going like this, the car has to bend towards the normal. So this was rarer because the speed was higher, and this was denser, medium. It bends towards the normal. So those examples of soldier and car are quite clear, right? Now all we need to do is link it up with light. Light is a wave, and when the wave travels, then there's a concept of wavefront. So let me draw a wave here. So for example, some waves on water. Those waves are going like this. If I draw lines like this, which are joining the peaks, those peaks are being joined, then water particles oscillate as the wave travels. So all the particles at this particular point of the water, the wave is traveling like this. The water particles move up and down. The direction of the wave is like this, and this line is perpendicular to it, and that is a line called wavefront. Wavefront is basically a line joining all the points where the oscillation is together. That is, all the water molecules, these three water molecules go up together, come to mean position together, and go to the negative extremity together. So they are oscillating like this. So we say that is together means in phase. So a line joining all such particles in phase is called a wavefront. I use the water example because all of us are familiar with it. In light, something else oscillates, electric field and magnetic field. Still, the wavefront concept still works, and the direction of propagation of the wave is always perpendicular to the wavefront. This is like the line joining the soldiers, and the direction of motion of the soldiers was perpendicular to that line. And that is why light has to bend, because light has got a wave character. So the fact that light slows down is due to its wave character, that is the interference of electric fields, and the fact that light bends because of a change in speed is also due to the wave character. So the bending occurs because the speed of light is different in different media, and the fact that light is a wave. the direction of propagation must be perpendicular to the wavefront. That is why bending occurs. And that is what is refraction. Now, why does it not bend if it is a perpendicular incidence? Say this is the interface between normal land and marshy land, and soldiers were marching like this. Okay, so at some instant, the soldiers are here. All three soldiers enter the marshy land together. So the line joining them is still parallel to their original line, and therefore they don't bend. Only for an oblique incidence they will bend. We are going to learn later that the speed of a wave is equal to its frequency times wavelength. What is wavelength? If I draw a wave like this is one wavefront, this is another wavefront. The distance between two wavefronts, that is called wavelength, indicated by the symbol lambda. And frequency means number of cycles per second. The oscillation goes like this, perpendicular to the direction of the wave. How many cycles are completed per second is equal to frequency. So the speed of a wave is frequency times wavelength. Frequency is decided by the source and it never changes. And every color of light has a definite frequency and therefore a definite wavelength because the speed of the wave is known. Right? Let's talk of refraction through a glass slab. So there is one ray coming in, we call it incident ray. This point is a point of incidence. It is coming from air to glass. Air is rarer medium and glass is denser medium. In glass, light slows down. In fact, light slows down in any medium. If it's going from vacuum, it is now coming to air, it slows down. From air to glass, now air and glass are two different media, it again slows down. So light slows down in all media, but how much it slows down depends on that medium. Compared between air and glass, the speed of light in air is more than that in glass. So I'll say the speed in air is greater than the speed in glass. That is why air is rarer and glass is denser. This is the incident light. This is the point of incidence. This is the normal at the point of incidence. Instead of going directly in its original direction, it must bend towards the normal. And this ray is called the refracted ray. Then it comes to another interface. The medium is again changing. This is glass air interface. Now it is going from denser to rarer. Instead of going straight, it must bend away from the normal. And this is the emergent ray. For a rectangular glass slab, since this line and this line are parallel, we find that the incident ray and the emergent ray are also parallel to each other. Although the emergent ray has shifted a little bit, there is a shift, parallel shift from here to here from its original direction. The angle between the incident ray and the normal is called the angle of incidence, and the angle between the refracted ray and the normal is called the angle of refraction. At this point, this will be the angle of incidence, let me call it I dashed. And because that is the incident ray at that interface, and this will be called the angle of refraction that we call R dashed. But from the geometry, we can see that R is equal to I dashed, and therefore R dash is equal to I. So magnitude wise, it is equal to R, and magnitude wise, it is equal to I for such a geometry. There are two laws of refraction. Like in reflection, we had two laws. Here also we have two laws. The first law is the same. Incident ray, refracted ray, not reflected now. Refracted ray and normal at the point of incidence lie in the same plane. And the second is very interesting. We have an angle of incidence and we have an angle of refraction. The ratio of the sine of angle of incidence to the sine of the angle of refraction is a constant for, it's not universal constant, it is a constant for a given pair of media. For a given pair of media, this ratio sin I by sin r is a constant, and it is also dependent on the color of the light. And this law is called Snell's law. So this is a constant for two things: a given pair of media. It is not a universal constant, and the color of light. And that is called Snell's law. So in this session, we learned about why light bends and also about the laws of refraction. In the next session, we are going to learn about Snell's law and the concept of refractive index.